Hello everyone, my name is Raluca Tarcan and I am from Babeș-Bolyai University in Cluj-Napoca, Romania. Today I'm going to present you a new fast and faster synthesis method for reduced graphene oxide in DMF, which is promising for future polymer-based composites. I will begin with a short introduction to tell you why we chose this method and why we chose DMF as a solvent. Then I will show you some experimental details regarding the synthesis of graphite and graphene oxide, which are the precursors, and then the synthesis method for reduced graphene oxide. Of course, I will discuss the results obtained after UV visible, Raman, and XPS analysis, as well as after microscopical investigation using techniques like scanning electron microscopy, transmission electron microscopy, and atomic force microscopy. Of course, in the end, the conclusions. Reduced graphene oxide is a two-dimensional carbon-based material with mechanical, optoelectronic or conductive properties very similar with those of pristine graphene. This is due to RGO's heterogeneous structure composed of a pristine graphene-like basal plane with few topological defects and highly oxidized regions. Although RGO can be rapidly synthesized from graphene oxide, shortly GO, in aqueous solutions, there is a still great challenge in synthesizing RGO in organic solvents. And this is why we chose DMF, because it is a polar organic solvent, it has a high boiling point and a surface tension of 37.1 millinewton per meter. According to the literature, the best solvents to obtain stable dispersions of graphene without any functionalizations or additives should have a surface tension in the range of 40-50 millinewtons per meter. On the other hand, graphene oxide has been reduced before in a mixture of water and DMF by a traditional synthesis method at reflux for 12 hours. This is very time consuming, so we have successfully managed to reduce graphene oxide in pure DMF in only 30 minutes by a solvothermal microwave assisted method without using any reducing agents or additives or functionalization techniques. Shortly, we have oxidized graphite to graphite oxide. Then we dissolved it in and exfoliated it in DMF in order to obtain graphene oxide, and then reduced it to obtain reduced graphene oxide. In more details, we have synthesized graphite oxide by modified Hammer's method, a protocol which can be found in the literature. Then we have dissolved graphite oxide powder in DMF in a concentration of 1 milligram per milliliter, exfoliated it by sonication, and centrifuged it in order to remove the graphite oxide that did not exfoliate. The resulting solution contains graphene oxide, which represents oxidized sheets of graphene, and it was introduced in a microwave reactor and left for 30 minutes at 120 Celsius degrees. UV visible and Raman investigation confirmed the success of the reaction. Firstly, the UV spectra looks a little unconventional because it shows the maxima corresponding to PP star transitions from the double bonds between the carbon atoms at 265 and 271 nanometers for GO and RGO respectively. In the literature, these have been reported to show up at 230 nanometers for GO and 260 nanometers for RGO. We have considered different reasons for this shifting. First was the solvent cut off due to the ability of DMF to absorb wavelengths lower than 275 nanometers, but placing pure DMF in the microwave under the same conditions as GO showed only a slight increase in the absorbance. Also, DMF has no influence in the absorption of GO or RGO. We also thought about the fact that DMF acts as an electron donor and forms a charge transfer complex with GO, which is a good electron acceptor. However, the most plausible explanation is the size of the flakes. The larger the flakes, the more shifted towards higher wavelengths the maxima appears. This is also in agreement with our SEM and TEM measurements, as well as we'll see further. Finally, what we see in the UVV spectra of GO is a shoulder at 300 nanometers, characteristic to NP star transitions from the double bonds between carbon and oxygen atoms. The shoulder disappears after the reduction, and the absorbance increase significantly along the whole domain, indicating the restoration of sp2 network together with the partial removal of oxygen-containing groups from graphene oxide surface. Raman investigations confirms as well that the reduction process occurred. The D band, which corresponds to the defects of the sp2 networks, and the G band corresponds to the in-plane stretching vibrations to the double bonds between carbon atoms, and the report between these two bands increased from 0.93 in GO to 1.08 in RGO. This shows that the defective domains increase due to the removal of the oxygenated groups from the graphitic surface. At higher frequencies, we have 2D band, and which indicates the number of graphene layers, and D plus D prime bands, which are visible only in defective structures. The report between 2D and G bands can potentially give information about the number of RGO layers. In our case, it is below 1, so it would indicate a multi-layer structure. The spectra obtained after X-ray photoelectron spectroscopy investigation shows for GO that the peaks corresponding to carbon, oxygen, and the simple bonds between the carbon atoms have the highest intensities. The intensity of these peaks decreased for RGO, while the intensity of the peak corresponding to the sp2 double bonds between the carbon atoms increased significantly, as we can see here. Moreover, the percentage of oxygen-containing groups decreased from 62% in GO to 28% in RGO. Also, the carbon-oxygen ratio in GO versus RGO increased from 0.61 to 2.52, which confirms again the removal of the oxygen groups from the surface of the graphitic lattice. The images obtained by scanning electron microscopy and transmission electron microscopy for a sample drop casted on a glass surface shows folded flakes with a wrinkled surface, randomly aggregated. The energy dispersive X-ray analysis showed the presence of some impurities from the graphite oxide synthesis, like sulfur, chlorine, or potassium, with no effect on the reduction process. Moreover, the carbon-oxygen ratio increased from 5.3 in GO to 7.9 in RGO, which again confirms the removal of the oxygen groups. The atomic force microscopy investigations performed as well on a drop-casted sample on a glass surface shows a multi-layered RGO structure containing around 11 flakes as high as 3.9 nanometers each. This is in agreement with the Raman investigation, when the report between 2D and G bands was indicating the same result. To conclude, we have successfully managed to reduce graphene oxide by an easy solvothermal microwave-assisted method without using any reducing agents, stabilizing agents, or functionalization techniques, and in only 30 minutes. UV visible, Raman, and XPS investigations confirmed the partial removal of oxygen-containing groups, while scanning electron microscopy and transmission electron microscopy showed folded and wrinkled RGO sheets randomly distributed. And as well, AFM images showed the multi-layer structures in a drop-casted sample. The presented synthetic method comes with a great potential for making RGO more solution processable in organic solvents, and thus it is promising for the development of novel RGO polymer-based composite materials that could be used in various applications. Thank you for your attention.